Hello and welcome to Skyworks Power over Ethernet Basics mini-series. My name is Bartomáš Botlik, Skyworks Staff Applications Engineer, and today I will give you a quick introduction about the PoE function called Maintain Power Signature. PoE PSE devices remove power if the current consumption of the port falls below a certain threshold. Its purpose is to ensure that the disconnected ports are not left powered on. To avoid power removal, PD devices can use a technique called Maintain Power Signature, or MPS in short. MPS has two components, a DC and an AC component. PSEs can monitor each of them individually or both. The two methods have their own criteria to maintain the connection. For the AC component of the signature, the PSE probes the port with a signal that has a frequency of 500 kHz maximum. In this case, the PD device shall present a valid AC MPS signature, which must be maximum 26.3 kΩ. For the DC component of the signature, the PD device has to provide current pulses at certain time intervals to show the PSE that it is still connected. It allows PDs to minimize their power consumption as no constant current draw is required. The limits varies between standards and therefore between PSE and PD types as well, so it is highly recommended to always design DC MPS with some margin. The newest IEEE 802.3bt standard introduced the so-called short MPS, which requires even narrower passes by the PD, minimizing current consumption even more. To indicate short MPS capability to the PD, the PSE provides a long first-class event. The following table gives a quick overview about MPS limits for the different standards and PoE device types. It is important to mention that these values refer to the input side of the PD devices. For the IEEE 802.3bt standard, these limits are assuming a single signature PD. For dual signature configuration, please refer to the corresponding section in the standard. Here, we are going to give you an example about the IEEE 802.380 MPS. The SI3406X portfolio adds only about 4 mA to the input current as it assumes a standby consumption of the host controller, which must be taken into consideration. If the overall consumption of the host device is standby current and the MPS passes are still below 10 mA, it is recommended to increase the standby consumption by adding an additional resistor to the output. This technique can also be used in devices to maintain the connection, such as the SI3404, where the MPS functionality is not available. Our SI3406X portfolio is capable of providing MPS passes in two different modes, in user mode and in automatic mode, which you can control by connecting the unslip pin on the chip at startup to VSS or VDD respectively. The first diagram shows the MPS sequence of the SI3406X devices in user mode. As the unslip pin is connected to VDD at T0 when the hot swap switch turns on, MPS passes are not present. After pulling the unslip pin to VSS at T1, the IC starts to provide the MPS passes at certain time intervals by adding 4 mA to the input current consumption. At T2, the unslip pin is pulled too high, so MPS is turned off. The application consumption starts rising at T3, and MPS is turned on again at T4 when the unslip pin is pulled too low again. As it can be seen, the MPS passes are entirely controlled by the host controller and the signal level of the unslip pin. This diagram shows the MPS sequence of the SI3406X devices in automatic mode. As the unslip pin is connected to VSS at T0 when the hot swap switch turns on, and the current consumption is below a certain threshold, the IC starts to provide the MPS passes at certain time intervals by adding 4 mA to the input current consumption. The application consumption starts to rise at T1 and it reaches the MPS off threshold at T2. The IC detects it and switches off MPS pass generation. If the overall consumption falls below the MPS on level at T3, the MPS generation is started again. The SI34071 is capable of supporting both IEEE 802.380 long and IEEE 802.3bt short MPS passes. As IEEE 802.3bt PSEs shall support short MPS, the SI34071 is capable of differentiating between IEEE 802.380 and IEEE 802.3bt PSEs based on the length of the first classification event and automatically adjusts the MPS length accordingly. The MPS generation is entirely controlled by the host MCU by sending a UART command to the SI34071. In this figure, a typical isolated UART connection between the host MCU and the SI34071 can be seen. To be able to adjust the additional current consumption of the MPS passes, an external resistor can be used indicated as RMPS in the figure. In the first diagram, a typical IEEE 802.3 long MPS turn-on sequence can be seen. At T0, when the hot swap switch turns on, N-sleep pin needs to be pulled to VDD. Long MPS pulse generation starts when the host controller sends the 04 hexadecimal command to the SI34071. Similarly, if the host controller sends the 05 command to the SI34071, the PD will stop MPS pulse generation. The second diagram shows a typical IEEE 802.3 BT short MPS turn-on sequence. At T0, when the hot swap switch turns on, N-sleep pin needs to be pulled to VDD. Short MPS pulse generation starts when the host controller sends the 04 hexadecimal command to the SI34071. Similarly, if the host controller sends the 05 command to the SI34071, the PD will stop MPS pulse generation. I hope you became a bit more familiar with the MPS functionality. For further information, please visit skyworksinc.com. Thank you and have a good day.